This type of questions is asked repeatedly. What is Joule-Thomson coefficient? This is the expression which repeatedly asked during the previous year exams. So let's discuss how this expression comes and how we need to write the answers and what are the other questions which can be asked from this topic. See, first of all, we need to understand what is the Joule-Thomson effect. Joule-Thomson suggests that when a gas or fluid, we can say that fluid, is allowed to pass from a high pressure region to a low pressure region through a porous plug. Its temperature decrease. And the decrease in temperature is proportional to the difference in pressure. So basically, this effect correlates how temperature get changed when the pressure of a fluid is allowed to change. So as a effect, what we observe cooling occur for most of the gases. Means when we allow gas to move from a high pressure region to a low pressure region, its temperature decreases. That is, cooling occur during this process. Now, for understanding this point, we assume a setup. There is a position A, which we consider as initial position of piston. And in this part of chamber, we take a gas having volume V1, initial temperature T1, and the internal energy of gas is taken as U1. Temperature of gas is maintained when a pressure P1 is applied on this piston. This gas allowed to move towards point V, and the volume of gas here is taken as V2, temperature is taken as T2, and the internal energy is U. We are assuming that the ball of this setup is taken adiabatic balls. That is, it is not transferring between system and surrounding. Definitely, we are taking P1 is greater than P2. Initial pressure is higher than final pressure of the gas. This is the basically low pressure region, and this is the high pressure region. And gas is moving in this direction. So let us take the point A. What is the work done by the gas on piston at point A? Let us suppose the work done is given by W1. That work will be P1 V1 because the volume changes B1 and pressure applied on the system is P1. We know that in chemistry, work done by the system is taken as negative sign. So we can say that W1 will be minus P1 V1. Now let us assume the point V. W2 will be minus P2 V2. W2 is what? W2 is the work done by the gas on piston B. W1 is the work done by the gas on piston A. So what is the net work done when the gas is allowed to move through high pressure region to low pressure region, net work done will be the W2 minus W1 final work minus initial work. So we can say that minus P2 V2 minus minus plus P1 V1. We can write this as P1 V1 minus P2 V2. Let us assume the equation 1. So this is the net work done when we applied a pressure at point P1 in order to allow the gas to move from point A, chamber A to chamber B, high pressure region to low pressure region. This is the net work done. Now, let's apply the first law of thermodynamics. We know that du is equal to Q plus W. But as we know that Q will be 0 as the process is adiabatic. In the experiment, you can say that internal energy changes from U1 to U2, that the net change will be U2 minus U1. And the work done from the equation 1 is given as P1 V1 minus P2 V2. Now separate the term. This is the enthalpy considered as final enthalpy. U plus PV is given as initial enthalpy. So there is a no change in the enthalpy of the process. So we can say that Joule-Thomson experiment is an isoenthalpic process. So this is the first important outcome which can be asked in the exam. Prove that adiabatic expansion, or you can say that adiabatic reversible expansion of gas is an isoenthalpic process. See, keep in mind that we cannot say enthalpy is constant throughout the process, because process is not in equilibrium completely. Although we can say final enthalpy is equal to initial enthalpy. We cannot say enthalpy is constant throughout the process. This is the first important result related to the Joule-Thomson experiment. Now, to find out the Joule-Thomson coefficient, we know that enthalpy is the function of temperature as well as pressure. Now differentiate this. On differentiating this, we get that dH will be differential of first function, assuming second function as constant. Similarly, partial differential of second function, assuming first function is taken as constant. For Joule-Thomson effect, we just proved that it's an isoenthalpic process. So we can put dH is equal to 0 in the above equation. See, We put the value of dH in this equation, as well as we know that delta H by delta T at constant pressure P is called as Cp. So put both these values in this equation. We just put these values in the above equation and separate the variable. You can write as minus Cp dt is equal to del H by del P at constant T into dP. From here, we can write dt by dP at constant H is equal to minus 1 by Cp del H by del P at constant T. This is the expression we want. In this equation, the rate of change of temperature with respect to pressure during an isothalpic process is called Joule-Thomson coefficient. We can write rate of change in temperature with respect to pressure during isothalpic process is called Joule-Thomson coefficient, represented as mu Jt. As the unit of Joule-Thomson coefficient is asked, we can say that unit of temperature Kelvin, unit of pressure will be atmosphere, Kelvin atmosphere inverse will be the unit of Joule-Thomson coefficient. So we can write the equation mu Jt is equal to minus 1 by Cp del H by del P at constant. This is the desired expression which is asked repeatedly in the previous year questions. Now, if we move further, we can change this expression into a different form which can also be asked in the future exam. We know that H is equal to U plus PV. So if you want to calculate del H, we can say that differentiate that equation. Again, from the thermodynamic equation, we know that du will be TdS minus PTV. So in place of du, we can write TdS minus PdV. This PdV will be cancelled out. We can write del H is equal to T delta S plus P delta B. Now, differentiate this equation with respect to pressure. Basically, we are trying to calculate the value of del H by del P. assuming temperature as constant. ds by dp at constant t, and the differential of p with respect to p will be cancelled out. We will get v. Now, by using Maxwell cycle, we can write that del S over del P by T is equal to minus del B by del T at P. This is S, P, T, B. We are moving anti-clockwise, so we can put the negative sign here. So we found that del H by del P at T will be we put the value of del S by del P in this equation. We found that it comes as minus T del B by del T at P plus B. Now we get the mu Jt in the different term. This is the value of mu Jt, which is commonly asked. But this expression can be asked this is another form of mu Jt. Now, we know that alpha is known as thermal expansion coefficient given by so if we want to calculate Jt in terms of alpha, we can put the value of del B by del T at constant pressure P. Taken V as common and multiplied by minus sign. This is the another expression of mu Jt. You can see the reference of K.L. Kapoor, in which we find these relations. So in future, maybe they ask prove that how we can get this value from this value. Now, although this experiment is done with the real gas, if you are talking about the ideal gas, see what happens. Although we can also prove by using that equations, but sometime they can ask separate proof for that. So I'm doing in a different way. We put the value of del H. We know that temperature remains constant. Now, del by del P, PV. These are the simple mathematical steps. In place of PB, we can put RT for ideal gas as temperature is remain constant. Now, this can be written as AB multiplied by delta B in denominator as well as numerator. We can get this. This term is taken as constant. We can put the value 0 here. Now see, del B by del P again have the value 0 as the temperature is also constant here. Zero at constant temperature for ideal gas. We can get mu Zt is equal to 0 for an ideal gas. Now, if we are talking about for a real gas, three important results we can get. We know that mu Jt will be the rate of change of temperature with respect to pressure during isoenthalpic process. We know that for Joule Thomson experiment, pressure is decreasing. We can say that delta P will be negative always. Now discuss few cases. Case 1. If T1 is greater than T2, final temperature is lesser than initial temperature. Means dt will be negative. So the ratio of dp by dt will be positive. Means if the temperature is decreasing during this process, the value of Joule-Thomson coefficient will be positive. In reverse, we can write that positive value of Joule-Thomson experiment suggests that cooling occurs. Now, taken as case 2, where both the temperature become equal. If there is no change in temperature, final initial temperature is taken as equal. We can say that isothermal process, mu Jt will be 0. So this temperature is called inversion temperature. What is it? Temperature at which neither heating nor cooling occur. Neither heating nor cooling occur. It's called maximum inversion temperature. Now case 3, where T2 is greater than T1, means delta T will be positive. Know that delta P will be negative. That is mu Jt become negative. If final temperature is greater than T1, means heating occur. So negative value of Joule-Thomson coefficient suggests heating occur. This will be the common case for hydrogen and helium at ordinary temperature. See, This is the important point. If a gas is moving from high pressure region to low pressure region and its initial temperature is greater than maximum inversion temperature, increase in temperature occur. This is the Joule-Thomson heating effect. These are the cases which is related to the value of Joule-Thomson coefficient. There is a one more important result which can be obtained by using van der Waals equation, value of mu Jt and the value of inversion temperature. This can be asked in the upcoming exams. We will discuss the separation, the proof of these equations in the separate video. Thanks for this. Hope you understand the topic well.